All right, in lesson 16 in module 1, we're going to continue talking about constants, but now we're going to be calling them something different. We're going to be relating them to scale drawings. And scale drawings are something, scale models are something we deal with a lot without even realizing it. So for example, this picture right here, I got it pretty small here, but this is actually a subway map. Now, some of you have probably been in the subway, or maybe not, or maybe to a train station or an airport or something, but they have big maps up, kind of showing you where the line, lines mean the subway line or the train is going. So obviously, this is a lot smaller than what we'd see in real life. And if it's a lot smaller, we say it's reduced, is another word for smaller. Okay, and there's a reason I bring up the word reduced. Likewise, when we look at this, we'll say it's a thumbprint right now. Maybe not a thumbprint. Let's say fingerprint, because it could be any of them. So this is a fingerprint. And if we've ever had our fingerprints taken, obviously, can't see me, but I'm touching it right now. It's a lot larger. It's a lot larger than what our fingerprint is. And so we're going to say this has been enlarged. And today all we're focusing on is understanding that sometimes we take things that are really big and we make them smaller. So if you obviously this map, any map is always going to be something a lot smaller than what we see in real life. Okay, obviously if you ever held a map of Michigan, I know we don't have that stuff very much anymore because we have GPS. But you couldn't be driving along in your car and open up a map that was the size of the state of Michigan. So what we do is we have a smaller version of it, and it's scaled down, it's proportional. And when I bring in the word proportional, now we are dealing with what we've been dealing with. Same thing with fingerprints. This is obviously a lot bigger. It's made bigger because it's hard to see. Somewhere along the way in your science classes, maybe you made a scale drawing of like an atom, right? Atoms are so small we can't see protons, neutrons, the nucleus. So you put it on a paper plate or something and you make it bigger. So we dealt with a lot of scaling, making things smaller, making things bigger. But you have to do it proportionally, which means we have to have a constant. And that's what we're getting into today. So if we look at these pictures here, don't overthink what we're doing. Okay? It says for the following pictures, A is the actual, and B is the drawing. So we have these pictures here of, and I know it's really grainy, just from the copy machine, and it wants to know if this is the actual size, is the drawing an enlargement or a reduction? Notice up here how I use the words reduced or enlarged. So hopefully you understand what those things mean. A reduction is going to be made smaller, enlargement is going to be made bigger. So if we just look at these two pictures here, to go from the actual to the drawing, we made it bigger. So this would be called an enlargement. And please, try to write better than me. I'm sorry. The same thing over here. This is like a ruler, and this is the actual, and this is the drawing. And so you can see that our actual is larger than our drawing. So we made it smaller, so it's a reduction. Again, don't overthink it. We're just trying to understand what's happening when we scale things bigger or smaller, because we're going to have to do it proportionally. So first step, understand if you're getting bigger or smaller. Second step, it comes to proportionality. One more example. It says, Derek's family took a day trip to a modern public garden. Derek looked at his map of the park. That was a reduction of the map located at the garden's entrance. The dots represent the placement of rare plants. The diagram below is a top view as Derek held his map by looking at the posted map. Okay, so he's holding his map. He's looking at the posted map. And what we understand is sometimes when we reduce things or we enlarge things, we can also rotate them. So if I couldn't get it transparent, but let's say I had this copy here, and this was the, let's see, this is the posted map, okay? And now we're going over here to Derek's map. Now I know we can't necessarily tell because I couldn't make it transparent with the tools I had available, but you can see that it's not necessarily matching up. Okay, so just kind of do your best to imagine. But notice when I spin it a couple times, sometimes we turn maps, you can see how the points are kind of matching up, even though I made them pretty small now. So we can see, okay, this is an R down here, P, W, and N. We can see that R matches up with A. So when we're corresponding points, they don't have to match up perfectly. Once we reduce or enlarge things, we can kind of turn it around. So point A right here is going to match up with this point right here, which was point R. I know it doesn't look like an R when it's that small. Point V is right here. Notice that matches up with point W. Point H is kind of right here in the crossroad, so that's point P. And point Y, whatever shape this is, it's on the edge of it, that's going to be N. All right, so again, don't overthink things, but what we're trying to understand is we can enlarge and we can reduce things, and what we're going to get into next is that being proportional. But even enlarging or reducing, we can still rotate and spin it. Kind of a real world example of how we use reductions and enlargements.